Welcome to Techonomics from Cyclotron Road. So you have a new technology and you want to model its performance and costs. Maybe it's a chemical process, or maybe it's a fuel cell electrode, or maybe it's a high-tech frisbee. There are lots of good reasons to build a model, like to show that your technology is economically viable, or to figure out where to focus R&D resources. Let's say that market research shows that we need to sell this frisbee for under $30 retail, and that for these types of products, retail is normally 5 times material cost. So the question is, can we make it for under $6 in material cost while maintaining performance? And let's say that to maintain performance, we need to keep the frisbee's rotational inertia within a certain range. This is our current product data. We have dimensions, densities, and costs for each layer. To model material cost and inertia, we'll first need to calculate the volume and mass of each layer. Modeling in Excel is fairly intuitive, especially if you've done other types of programming before. Chances are you already have some experience using it. This video series will teach you best practices and techniques that will help you build models that are better for communicating with your colleagues and investors, and that will let you more efficiently explore the factors that drive your economics and performance. You can also download these example workbooks to follow along or use as templates. Now that the calculations are complete, I'm going to add some formatting to make the spreadsheet easier to use and interpret. This will include some special formatting to differentiate our input values, and some conditional formatting to alert us if our results are outside of their acceptable range. So it looks like we're coming in a bit over the $6 target. Graphs can help to make data more tangible. This pie chart shows the distribution of layer costs. It's pretty obvious right away that this outermost green layer is the most expensive. And that makes it seem like a good place to start looking for improvements. Let's see if we can make it any thinner while still maintaining performance. Not really. What if we tried some alternative materials? I'm going to add a table of 3 possible green layer materials along with their densities and costs. And then I'll add some formulas to the original table that will automatically update when I choose a material from a drop-down list. Excel is often the best tool to use for early-stage cost modeling. For one, it lets you communicate across disciplines and organizations. Virtually everyone in the business world has Excel and knows how to use it. It's also flexible. In early-stage modeling, you need the ability to zero in on the factors that make your innovation special, while at the same time making broad generalizations about others. So this is our original material, and now here's the Superspeed polymer, which has a higher density but also a higher cost per kilogram. With this polymer, we can drop the thickness to just 1.2 centimeters, but the higher cost still leaves us above that $6 mark. Now let's look at this polymer called Superspin, which is somewhere in the middle for both density and cost. We'll need to bring the thickness back up again to raise the inertia. And it looks like at 2.7 centimeters we can hit the mark for both inertia and cost. We'll still probably want to test some prototypes with this new material, but this Superspin polymer might be our ticket. As you can see, a well-built model is much more than a one-off cost estimate. It's a tool for understanding the implications of all that you currently know about your technology and for communicating them to your colleagues and investors. This was an example of a bill of materials approach to modeling. In the next video, we're going to look at modeling a manufacturing facility. You can download this video to use as a template from the Techonomics website. You'll also find other videos and resources there. See you next time.